Hello, Jordan.
Hello.
Hey, how are things at your end?
They're going. It's been a wild ride.
It's a while what?
I said it's been a wild ride this semester so far.
Yeah. So are you still good, right? Like no symptoms or anything?
Currently, I feel fine. As in, I don't, it's possible that I've come in contact with it, but whether or not I get sick or not, I guess to be determined.
Yeah. Must be stressful anyway, right? Someone in the family, like, I don't know, so many things happens around this.
There's a lot of things about it that are pretty stressful. I think it's just, that's the world we live in today. And what can you do? You gotta just keep chugging, doing what you can. I think my wife has, she felt like she was getting better yesterday or the day before yesterday. And then yesterday, I think was her worst day so far. So not really sure if she's going to be getting better yet, or we'll see. She can't taste or smell anything.
Oh.
She didn't know if she had it at first because she has like a lot of sinus pressure and congestion, and I think she said the biggest thing is like she's just super tired. She's very fatigued.
Yeah, any sickness scares you, and this one is more stressful because you feel that there is no medicines and all that.
Yes, yeah, exactly. Yeah, there's not much you can do about it. You just gotta, wait it out. And hopefully you're a healthy enough person that you don't have any severe reactions or anything. So I don't suspect anything, serious with my wife, but you never know, I guess. We'll just have to wait and see, and hopefully I stay healthy. I mean, that's the big thing because I'd like to complete everything.
Yeah.
Yeah, I was wondering, Jordan, if you're still able to work.
What's that?
I was wondering if you're still able to work.
At home? No. Once you get tested, they essentially what they do is they contact the health department, and then the health department contacts you and tells you how long you have to be quarantined for and how long you can't do anything, basically. So it's basically a doctor's excuse for everything. And actually, I didn't know this, but it makes sense when you think about it. When my wife got tested and she tested positive, likely she only has to, her quarantine isn't as long as mine is, because since they know from the first symptoms she showed of having it, there's like a 10-day period from the time that she first showed symptoms, because there's like a period before that, which could be anywhere from 2 days to 2 weeks, that she probably came in contact with it before she actually showed symptoms. So
yeah,
her quarantine is only 10 days, and mine was 14.
okay,
Yeah.
gotcha. How far along in those 14 days are you?
Well, she got tested on Friday, so it's from the time that she showed symptoms, because I think that's whenever she would become contagious. So I think she started showing symptoms. The earliest we noticed was Thursday, I think. Thursday or Friday. So I'll be in quarantine until basically a week from today.
Gotcha. And that's assuming you don't show symptoms also.
Yeah, if I show symptoms, then I guess would have the 10-day deal, because I suppose there's also that 2 week time period where I may not show symptoms but have gotten the virus. So we'll see.
Gotcha.
I guess the longest it could probably be would be a month. But yeah, it's weird because we're completely out of groceries, so we had to order groceries online and have them delivered to our house, which is very strange. And then the guy knocked on the door and we were like, yeah, you just have to leave all the groceries on the doorstep because my wife has COVID. And you feel like a leper,
Yeah. Oh man. Yeah. Well, hang in there.
Thanks, appreciate that. It's gonna keep grinding.
You got more time to focus on school.
Yeah, that's one thing that when I emailed Shajesh, I said that I'll have a little extra time, believe it or not, to work on some things, as long as nothing bad happens or I feel like I have to attend to my wife more. We'll see.
Yeah.
But in terms of time in the day, I definitely have more time, not doing other things. So.
I hope that's
there's added stress though when you think about money.
Well, sure, yeah, there's that too.
Okay. There was a homework due today, and last homework is due 2 weeks from today, and so all submissions have to reach me. December 4th.
When are you going to post the final?
Weekend maybe, or yeah. When do you guys want?
I'm not sure. I was just curious.
Since this is Tuesday, usually what I do is that I post it during the weekend before the finals, and then you have time.
Yeah.
But typically that's about Thursday or something, and you have 4 days. But this is Tuesday, but still you have about 2 days or so. So yeah, I should be able to post it by end of Saturday. Depends how Thanksgiving goes. If I can work during that time. So. I did think of one question, which is what you asked last time, right? So I think I decided to put that on. Or what I can do is, as I put the questions on, it can keep getting updated. If that is okay. I don't do that because it might be confusing for students that they will, someone shouldn't work on 3 problems and say that, oh, I thought there are only 3 problems, 2 problems came afterwards. So if you guys are ready to accept that it could be updated until the Saturday before the exam, then I can keep doing it and post it and you can keep working on it. Does that make sense? Do you guys prefer that or?
I mean, I'll take any questions as early as I can get them.
Yeah. Okay.
From
So,
a
yeah.
convenience standpoint, it doesn't seem like a big issue for me.
I think this class, I don't see any issues coming up. Typically, it's just as a safety thing that no one should come back on me saying that you work on one question and that, oh, that's how it is. So yeah, sure. So I'll put this question out as soon as possible and make it available. Okay.
Maybe once the whole test is fully updated, you can just put a note on it at the bottom or something.
Yes, final
These are all
version.
the questions.
Yeah, final version. Yes. Yeah. Good point. Yeah. Okay. I want to do a spherical harmonics. It's pretty much very closely related to legendary polynomials. So, and we did not do a lot of it when we were doing electromagnetism. We only touched on it. We used the basic identities. So a few things on that. So basically prove a couple of identities on legendary polynomials. That's something I want to work on, and do what we have here. So I want to begin by reminding ourselves of what legendary polynomials was, and there was this dipole moments structure we saw. We want to do that and barely at least introduce what the motivation of spherical harmonics is. And in the next class, we will actually come and do the recurrence relation or generating function for spherical harmonics, where we really get the definition of it. So very broadly, this is spherical harmonics, motivation, and it's pretty much legendary polynomials with a little bit of other azimuth angle also coming in. Let's begin by remembering that we have let's say a charge at the origin. So a 1 over r potential, right? We don't have to have charge. So 1 over r potential. That means point charge at the origin or a gravitational potential due to a mass, point mass at the origin. Notice that it doesn't have to be really a point mass, even for a sphere, even for a spherical mass distribution. So this was a positively charged sphere let us say of radius r. If you're outside, if you observe this outside, that's your vector r, and this is origin, right? So that's origin. Okay, and let's say this is a shell, then we know that electric potential due to this shell, so this is a spherical shell. That means it's hollow, right? Hollow inside. Then we know that the electric potential due to this is given by, and if it was gravitational, there's a corresponding expression there. It's just this gets replaced with G. And this is Q over R, just the magnitude of the vector. If you're outside the spherical shocks, and if you're inside, that's 0. 0 inside. That's a little remarkable statement in the sense that it does not depend on the radius r, which means that if I were to change the radius, I make it smaller or bigger, this will remain the same, right? So it's independent of that. And in that sense, you can take it all the way to r tends to 0, and you can think of it as a point charge and still get the same expression. So this is correct to say that since it is independent of r, make it a point charge or a point charge. You have 5r is equal to 1 over 4 pi epsilon naught q over r, as far as r is not equal to 0. Or not equal to 0. So that's for a point check. What does it satisfy? It satisfies the Laplacian. So there's a Laplacian. It satisfies minus square over 1 over r is equal to 0. And we again, this is r not equal to 0. If r was equal to 0, this will be an infinite quantity, and you can use Gauss's law or the divergence theorem to show that, oh, this actually, when you add up all these points, this is not really 0. So that's a delta function, but we don't want to spend too much time on that. We are going to be staying r not equal to 0 in this whole discussion. So it's beyond that point r that we are interested in. We made one point that suppose now I were to move this, like remember how we, or let me go there, let me not go there at all. Since this is 0, I can actually apply, operate a vector, or have an operation of A dotted with del. And just for consistency with some other concepts that we have learned, there's a negative sign. It doesn't really matter, even this negative sign, since it is equal to 0, it doesn't really matter. Let me operate this expression with this operator. So that's minus, so that's minus del square and 1 over r. So I take this expression and operate it on with a directional derivative. So this is a gradient. So this becomes a directional gradient. Gradient can apply in all directions, but we are specifically asking what's its derivative in a particular direction. So it's a directional derivative. Since it was 0 to begin with, if I were to operate this on the left hand side, when I operate onto the right hand side, that will be 0. But there is one more thing we can say. If A was a constant vector, this can go through this Laplacian, and I have a relation that minus A dotted with 1 over R is also 0. And why is that? Because I'm saying A is a constant vector. The gradient operator commutes with the two gradient operators that builds the Laplacian, so it can go through. That means the statement is that if 1 over R is a solution of the Laplacian, the operation of a directional derivative of 1 over R is also a solution of the Laplacian. Right? That's how we motivated this multiple expansion. So what is this equal to? Let's evaluate this quantity so that then we know the solution. Correct? So let's evaluate del of 1 over R. So that's equal to, that's an electric field, right? If there was a negative sign, that's an electric field. So that's minus R hat over R square. Right? The divergence of electric potential due to a point charge is the electric field, but there is no 4 pi and epsilons are not there. So that's how it looks like, and we will write this as, oh, that's no minus, right? That's plus, electric field is plus. So that's plus vector R over R cubed. So A dotted with del 1 over R is equal to vector A dotted with R over R cubed. So that's also a solution. Okay. Over R cubed, that's equal to 0. We said this is L equal to 0, the first solution that we found, or of the Laplacian, that's for L equal to 0. And here we will say this is L equal to 1, that's for dipole, right? That's a monopole, that's a dipole. That was our labeling process. Again, we are looking for solutions for the Laplacian. That's one solution, that's second solution. And if I can operate it once, I can operate it second time also, right? So again, operate it. So let me, so minus A dotted with gradient. And this time, I can even put in another constant vector, right? This is some constant vector. Let me say this is A1 and this is A2. So directional derivative in two different directions. And again, notice, maybe I should point out before I proceed, that this is also radius dependent. Like this could have been on a finite radius. There is an outside, there is a structure, there is an inside, there is a structure. We are making it a point dipole and saying this is the electric potential due to a point dipole. Same thing in here. So this is minus del square. That's also 0. Again, the gradient operator goes through. It will go in, and I'll have this minus A1 to the del. That's 1 over R. That's equal to 0. We have already operated this, so this is a new solution we have, right? So we just need to find the structure of this. We already know what the structure of this has, so that's A dotted with R. We just have to operate it with another operator. We have minus A1, you know. So directional derivative in two different directions, A1 and A2, times 1 over R is equal to minus A1. This one we have already done. It's A2, let's say. And after we operate this, we know what this is going to be from the multipole expansion that we have encountered. That's nothing but the electric potential due to a quadrupole moment. But let's operate this just for completeness, just to see the pattern that's emerging. So the gradient operator has, let me say this is minus A1 dot, and the gradient operator can act in the numerator, then it gives me a 1, so that's A2, vector A2 over R cubed, and when it hits the denominator, I have minus 3, and then operate it with R raised to 4, so that's R raised to 4, and then there is R hat times A2 dotted with vector R. Again, make this a vector R, so that's R raised to 5. And this is nothing but, this becomes a plus. So that's 3 times vector A1, 2 dotted with R, and then minus of R squared. Let me write it as A1 dotted with A2 times R squared divided by R raised to 5. Little bit of review. So this is L equal to 2. So this is also a solution. So that means gradient, the Laplacian of this whole quantity. So, like that. So it's 3 times is equal to 0. So that's a new solution you have, and that's L equal to 2. Quadrupole moment. And this clearly gives us an idea of how to build more and more solutions. I keep increasing my L, I get more solutions, but we need some way of organizing them, right? So surely L equal to 1 is a solution, but then right here, right, we have other ways of writing this. It's not really necessary that I should have all the components, right? Each vector component is a solution, right? Here, if I forget about the R, each component is a solution. If this is a vector that is a solution, each component must be a solution. So it seems to suggest that L equal to 1 will have 3 pieces, like 3 different solutions. When L is equal to 2, similarly, so if I were to not worry about A1 and A2, they are constants. So that's a dyadic. So that seems to suggest that there are 9 components here. So if I were to remove the A1 and A2, what's remaining is a dyadic. That is that there are 9 components, but are they all independent? That will be a it will be a symmetric dyadic there, and each one of them, if if a dyadic is a solution of the Laplace, in each one of them is a solution, and we want to actually find a way to actually classify them, like each one of those components out there. So that's the idea there. But first, let's try to at least explore how many components are there. Like here, it seems like there are 3, and how many are there in here? So how many independent solutions can you think of? That's what you want to ask. You're asking how many independent solutions can we construct for each L. Right. So given an L, so let us say L equal to 2 and so on. So when there is L equal to 2, you see that in the numerator there are 2 R's. When there is L equal to 1, there is 1 R, and L equal to 3, there will be 3 R's. So it seems like so L equal to 1, so there is 1 R. L equal to 2, there will be 3 R's multiplied. No, 2, right? L equal to 3. And so on. Each vector contributes either an X, Y, or a Z if you think of it in rectangular coordinates. So when you are collecting all of them, so there could be so X raised to, if I multiply L R's, I will get X raised to say, let us say K1, Y raised to K2, and Z raised to K3. So from each vector, I can get a component, a rectangular component, but the total has to be K1 plus K2 plus K3 has to be equal to L. That tells us that there are that many pieces of R that's there. So we're multiplying R, L vectors, and if you think of it from rectangular coordinates, each one will provide a K1, but the constraint is that K1 plus K2 plus K3 has to be equal to L. So, so it's a homogeneous polynomial, right? That's what you would say. So if you multiply R squared, for example, R times R, each one of them, so there are how many pieces in this? This will be X times X in the I hat direction, plus X times Y in the I hat J hat direction, plus X times Z in the I hat K hat direction, plus so on. So this is plus Y times X, J times I, plus Y times Y, J hat. Let me do this. J hat, K hat, and plus Z times X. K times K. But clearly, these two are the same. These two are the same, and these two are the same. So you get rid of them. Like we want only the independent ones. So out of the 9 components, it seems like there are only 3 plus 3. There are 6 of them that are independent. Similarly, in general, if the total was K1 plus K2 plus K3, how many can you build out of that? So first you let us say first fix K3, and then K1 plus K2 has to be. So how many can you build? Oh, so let's fix K3. We're just finding how many components are there in a general L rank, right? For L equal to 1, that is 3, L equal to 2, that seems to be 6 in this way of looking at it. And how many there are, right? So fix K3. If I fix K3, K1 plus K2 has to be, so that means K1 plus K2 has to be equal to L minus K3. There are how many ways I can construct that? It is exactly L minus K3, right? So if the maximum it can go is L minus K3, I can, once I fix K1, K2 is fixed. So it is L minus K3. And that I have to sum from K3 going from 0 to L. Is that correct? But this is not L minus K3, right? Yeah, K1 plus K2 is L minus K3. But when I fix that, X and Y, because there is a 0 also allowed, so there is a L minus K3 plus 1. That's the number of pieces. Just counting there. And that gives me, this is equal to, to count this, so it is L plus 1 times K3 to L, so 0 to L, right? So it is L plus 1 again. And when it is minus K3 going from 0 to L, so that's L into L plus 1 over 2. Okay, that's what it is. So this is equal to L plus 1 times L plus 1 minus L over 2. And that's equal to, how much is this? So L plus 1 times L over 2 plus 1. And that's L plus 1 times 2L plus 1 divided by 2. That's the number of components you can build when there are L equal to, so for any general L. But we also have to notice that there is further constraints in the sense that this satisfies the Laplacian, right? Very broadly saying this is a solution of the Laplacian, so this is equal to 0. So that gives us some equations. So since we are bringing down 2 powers, so there are how many constraints here? Each of this component, when you take the derivative 2 times down, there are constraints of that. So if you want, this is L minus, so L minus 2 similar equations, constraints. L minus 2 polynomial constraints. That means to say that if I have this many independent ones, there are that many with L minus 2, I have constraints. So the free pieces would be, I will subtract this for L plus 1 times 2 L plus 1 over 2, and then minus of, start with L, bring this down, right? So L minus 2, so that's L minus 1 times 2 times L minus 1 plus 1 over 2. It may not be very clear what I'm doing, but I'm just deriving how many free components there are, and as we proceed, hopefully that will get much more clear. So this is what is this? 2L minus 2 plus 1. So this is 2L minus 2 plus 1. So that's minus 1, 2L. -1, and how many of that? So, easier way to do this. Okay, just multiply it, I guess. So it's 1 by 2. So that's 2L square plus L plus 2L plus 2. 2L square plus L plus 2L plus 2, and minus of 2L squared minus L, and then there is minus 2L, and then plus 1. Plus 1. Oh, what did I put 2 here? Plus 2L plus 1. Okay, 2L squared cancels out, and 1 cancels out, and what I have is L plus L, 2L plus L, so I have exactly 2L plus 1. I think so. Okay.
How did you get 2L plus 1 then?
12, because I have 2 of them here, plus this, and that divide by 2. So 2 of them divide by 2. That's 1. Right? So there's a 2L plus 1 here, 2L plus 1 here, divide by 2, right? So 2L plus 1.
Oh, I thought it was 2L plus L.
Oh, that's what I was just, okay. 2L plus L. Yes, that's 2L plus L. Okay, check again. It should be 2L plus 1. Let's see, 2L plus 1. Wait. This we did it correct, right? Okay. Yeah, this is L plus L, right?
Wait, I think
Did I multiply this correct?
in the line above, like L divided by 2 plus 1 should be
L divided by,
in the line above.
oh, here.
Yeah. So that second term,
Oh, L plus 2 over 2, correct? Oh, yeah. Okay. That's the, okay. So then I have to do everything. So that's L plus 2 over 2, right? Okay. Thank you. Okay, so this whole thing has to be redone. Okay. Okay, let's do this again. So this is L plus 2 over 2 minus, we're doing L minus 2 now. So that's L minus 1, L minus 2. So that's L minus 1. That's L minus 2. So that's just L divided by 2. So L plus 2. So that's L. Yes. Okay. Let's see this time if we can get this in. Okay, so this is equal to 1 by 2 L squared plus 2 plus 1, 3L, right? This time again, 3L is there, plus 2 minus L squared, and then there is plus L, minus L, which is plus. Okay, let's try this again. So that seems to be correct, right? So that's 4L plus 2 plus 2. Okay. Better. That's cheating. Okay. Good. Okay, that helps. So we have 2L plus 1 components, and the goal is, so this is what we are going to, so apparently whenever we say there are so L equal to 2 is a good example, right? So this is the motivation. So minus del square of the structure in here that we saw 3 times A1 dotted with R, A2 dotted with R minus A1, A2 R square over R raised to 5. This can be broken into 2L plus 1, so it is L is equal to 2, so there are 5 pieces in here. So 5 independent pieces as far as components goes. And as you get higher and higher, there are more and more independent pieces. So this is what we were going to call, so this will be called Y L, right? So L is equal to 2 now. And each of these 5 pieces, we want to call this M. L is fixed, so for given L, M is going to go from, so M will have 2L plus 1 components. And that seems to be a familiar idea. If you have seen any kind of quantum mechanics, you would say that, oh, M, a good way to run the M would be to, M can run from minus L, minus of L minus 1, all right, minus L plus 1, and so on. You'll reach 0 and then keep going, and that is L minus 1, and then L. So that's the way to run it, but we are not going to impose all these things right away. This is just to give you a feel that whatever is there in this, we want to break this into that many pieces, and that will be what is called spherical harmonics of order L and order M. L is the whatever we talked about, and M, the 5 independent pieces, is what will be represented by M. What does it depend on? It will just depend on the angle. So notice that when we say A dotted with R over R cubed, right? Or 1 over R is a good example. It doesn't matter where you are on that sphere. As I said, it can be a point charge or a sphere. The radius of the sphere is not really important. It is the direction that is important. So in that sense, Y, L, and theta will be only a directional quantity. So that's R hat. So it will depend only on R hat. Or you can say this is theta phi. It doesn't mean that there is no R at all showing up. Whatever is there as R will be pulled out as 1 over R raised to 2L plus 1. Right? So this will be the solution. So if once we can classify this, so solutions of Laplacian very qualitatively seems to be YLM theta phi divided by R raised to 2L plus 1. For each L, L is equal to, so for each L, L is equal to 0, 1, 2, and so on. And M goes from minus L to plus L. That's all what we are trying to do, but we would like to get a clear expression of YLM. All this is to sort of motivate what we are doing. So let's have a clear picture of how you would construct YLM. So let's begin again, a little more rigorously. And so let's also notice that, let's see. So let's try to see what is del. So we want to talk about A dotted with vector R raised to L. So that is what our concept of is it R hat or I'm not sure. Yeah. Okay. Right. Yeah. So that's going to be our construction, or this will be our generating function. Let's say this will be the generating function. Remember, whenever we have special functions, we keep a function that's of interest and then expand it as a series, and the coefficients are identified as our function. So that's A dotted with R with L, and let's see if this is a solution of the Laplacian at all. So let's check what is del square of A dotted with R L. So we want to ask, is this 0, right? Is this 0? So that's a question. So let's do the first derivative first. So this is gradient of A dotted with R. So that A dotted with R raised to L would be equal to L times A dotted with R times L minus 1. Right? That's how you take the derivative. And then you have to take the derivative of whatever is there inside. So that's a gradient of A dotted with R. Let me write it as R dotted with A. That lets me identify that, oh, there's a completeness there. That's 1. It's a completeness relation of our vector space. So that's equal to, so that's just vector A, right? So that's L times vector A times A dotted with R times L minus 1. That's good. And remember, A was a constant vector, right? We're not changing in time. It's not a position dependent constant. That's gradient. Put one more. So del square raised to L is it goes through all the way, and you have to take a dot now. So this is minus L A dotted with gradient of A dotted with R raised to L minus 1. Again, do the same thing that we did earlier. So that's minus L times L minus 1. So that's A dotted with whatever is there after you operate this, right? So this is L minus 1 comes down, so then that is A dotted with R L minus 2. And again, the gradient operator, which is supposed to go in here, dots with R dotted with A. Unlike last time, what we have is that earlier when we were doing, there were distinct vectors, right? A1, A2, A3, there were distinct ones. These are the same A's that are showing up. So again, there is this one comes in, but if that is 1, that's a vector A that remains, and that operates with this. And we have minus L times L minus 1 times A dotted with R raised to L minus 2 times A square, the magnitude of the vector square. And again, we ask, our question was, is this equal to 0 or not? Apparently, it's not 0, right? We would like this to be true for each L. So this is not 0 because if you begin with something 0, then that's not an interesting solution. So a non-trivial solution requires that A square should be 0. So that should be a vector A whose dot product has to be equal to 0. If you want it to satisfy the Laplacian. So if you want this, because we are going to build spherical harmonics out of this, we would like this to satisfy the Laplacian. So let's say that this does satisfy the Laplacian. Let's begin by stating that we would require this to be a Laplacian. If that is the case, then we need this to be true. And that raises the question, what is the vector whose dot product with itself is 0? Right? Does that exist such a vector whose dot product is equal to 0? And a quick thought will tell us that no, right? That's not possible. So that implies that the x component squared plus y component squared plus z component squared is equal to 0. So that's a sum of three squares equal to 0. Three squares are positive numbers, and that cannot be true unless the vector A is 0 itself. Again, if vector A is 0, then that's a trivial solution because you begin with the 0. Of course, 0 will satisfy a differential equation. So we are sort of stuck here, but then we give it the room that we just came up with vector A, right? This is an arbitrary vector. It can be complex. Right? Suppose it were complex, then that's possible. Then you can. So now we are going to talk about a vector A. So that's so real components of A doesn't help. So we say that let A be complex. That means to say that its components AX, AY, and AZ are complex. Right? A1, A2, A3 are complex. And still, it has conditions to obey, right? So let's say, so now A1 is equal. So A1 square plus A2 square. So what do I want to define here? Oh, so I want to define, yeah, so since they are complex, so this is going to be defined as, how can I motivate this? So let's say, so to begin with, vector A is equal to A1 I plus A2 J plus A3K, right? So that's, and allowing A1, A2, and A3 to be complex. Then I have yeah, I'll keep everything general. Yeah. So yeah, so now notice again A1, A2, so that means to say that A1 is, for example, A1x plus I times A1y, right? So the three components there, A2 is A2x plus I times A2y. This I is complex number I, and this is ijk, so there should be no confusion. There are 6 pieces in there, just to clarify. But we'll never break this up, so that's what I was a little confused there. So we have A1, A2, and A3. So let's redefine, right? We would like something better. So let's say this is A1 plus I2. In fact, A1 minus IA2, I'll define as y plus square. Again, y plus is also complex. And A1 plus IA2 is y minus square. So that's just a relabeling I'm doing instead of working with A1, A2, I'll do work with y plus y1. What is the motivation here? Notice that this is being done. Have you guys done harmonic oscillator in harmonic oscillator in quantum mechanics? As ladder operators, how many of you are familiar with ladder operators in harmonic oscillators?
We briefly covered that in my undergraduate course in Griffith's textbook.
That's good. Aliyah, familiar?
Yes, I'm familiar with that. Yes.
Yeah. Michael?
It's not ringing a bell for me.
Oh, okay. Okay. So, yeah, how about this? Is this familiar that harmonic oscillator has many states? This is 0, ground state, first state, second state, and so on, right? And you would like an operation to go from one state to the other. So you would say A dagger times 0. I don't want to say y, so I want to say y dagger, right? Y dagger 0 will be some constant times 1. Okay. Y dagger square will be equal to 2 as some constant, let's say C. So this can depend on Cn. Right? So this will be Cn, C minus 1. As some constant, let's say proportionality. So this is clear. Okay, roughly, if that is that familiar, right? So that's what are called ladder operators. There is an operator that takes you up, goes up. There's another operator that brings you down. So then you can do all of harmonic oscillator using algebra pretty much, rather than differential equation. And we will show that it depends. I don't want to say we'll show y plus y minus have a cushion. But y plus y minus will have connections with these dagger operators. And that is why we are actually defining it. That here it might seem like this is just coming out of nowhere, but there is a connection which is not transparent right away. Remember that how do you say this? Extra credit, right? So what are the solutions for harmonic oscillator problem in quantum mechanics? Is that clear what I'm asking?
Could you say it again, please?
If I have a harmonic oscillator, what functions or solutions describe the wave functions in quantum mechanics? Which functions describe solutions of a harmonic oscillator problem. That means the energy eigenstates of a harmonic oscillator are described by which functions? So extra credit. Extra credit. Where's that? Yeah, here, extra credit. No. So eigenfunctions, energy eigenfunctions, energy eigenfunctions of harmonic oscillator are which function are which just name them, right? But that's the first question. I expected this to be easier, right? These are Hermite polynomials. Have you guys heard of Hermite polynomials? It turns out to be Hermite polynomials. But the next question is the more relevant problem is that a system that is conserving angular momentum, right? A system that conserves angular momentum. How will you know that angular momentum is conserved in a system? Let's say in quantum mechanics, you write a Schrodinger equation, you have a potential, and you want to check whether it conserves angular momentum or not. How will you know? It is done by looking at the spherical symmetry of the potential. Right. So this is so if it is spherically symmetric, if potential is spherically symmetric, then angular momentum is conserved. This you will see in classical mechanics. If you have taken classical mechanics, you will be roughly, at least like proof depends on how far you get into the course, but at least this is motivated. That's good. So what is linear momentum then? So linear momentum is conserved. How will you check that? So spherical symmetry involves angular momentum. Linear momentum would be which symmetry? It would be translational symmetry. If you were to move your potential translationally, so this will be translational symmetry in space. And there is energy also conserved. Energy is conserved, is decided by translational symmetry in time. So that's the same as, remember when we were doing electromagnetism, we were saying, oh, check for if this is the case, go to Fourier space. Why Fourier space? Because those are the solutions. You look for the solution. So the question I was asking is, if a system conserves angular momentum, that means it's spherically symmetric, then what are the solutions? You immediately expand the solution in terms of spherical harmonics. Whenever you have a spherically symmetric potential, you will look for the solution in the radial component, of course, but its angular solutions will be spherical harmonics. So solution will involve spherical harmonics. And so still, so I'm motivating why it is plus and minus, right? That's what I'm trying to do here. But still, that spherical harmonics, why worry about harmonic oscillator? Like the dagger operators are for harmonic oscillators. So why worry about the ladder operators when we are working with angular momentum? And the point is that angular momentum can be thought of as two harmonic oscillators. So that is a nice thought. This I can get rid of. So.
Excuse me, could you read the questions again?
Oh, could you read
Because they are not.
Okay, let me zoom.
Good.
Is it better?
Yeah. Thank you.
Yeah. Me writing small doesn't help. Okay, so I think with this, so here is the motivation. So harmonic oscillator, very intuitively has the following eigenstates, right? So there is 0, that is 1, that's 2, and so on. But that should be very straight. Whenever you see equidistant states in quantum mechanics, that's harmonic oscillator. Angular momentum, on the other hand, has only 2L plus 1 states, right? For a fixed L, so there are 2L plus 1 states. So what you would do is you build another harmonic oscillator, but this time do this in the opposite sense. So this is 0 prime, let's say 1 prime, 2 prime, 3 prime, and so on. Okay. But it is not at all obvious that just because the number of states you can count this way should give you that. It is not obvious. One thing is clear, that what you do is that there is a dagger operator for here, there is a lowering operator for here. So here there is a raising operator, here there is a lowering operator. But if you cross these two, since you cannot go below this, this picks out a finite number of sets. Right? So this is 2L plus 1 states. So the idea is that angular momentum can be written in terms of two harmonic oscillators, and this is usually written as SU2 yeah, SU2. How do you say this? I don't know which group it is. Yes, I forgot. Yeah, so let me not say it. I think the point is angular momentum is SU2, which is related to SO3, and it can be written in terms of two harmonic oscillator groups. And I think it is SU1, but I don't want to say it. Okay, but I'm not very sure. So whatever the group representation is for harmonic oscillator, it can be written in terms of two harmonic oscillators. So anyway, so the extra credit is for you to find, or what is that? Show that or realize that angular momentum solutions are given in terms of spherical harmonics. And that sort of motivates why we have dagger operator. And from there, I will build on to this. So yeah, I stop at a not a very convenient point, but I think that I'll go back a little and then start over. So good. Okay. Okay, thank you. And have a good small set of holidays. Yeah. I'll be sending you guys an email, by the way, to just for a hangout on Tuesday, which is long pending, but I'm sure after today I'll have more time. Okay. And again, it's optional. You guys come or not. Okay. Just hang out on Zoom. Okay. Enjoy, guys.
Do you know if Alan is going to be able to come?
Yes, I did have a chat with his wife. So she said that he comes for about 5 or 10 minutes, and depending on how strong he is, he will carry on with it. So she wanted to know the time, so which is promising. Right? So she said, give us the time, and we'll try. And the question is, how long can he stay? Most
Sure.
probably he'll be there, but then he gets tired after he talks for a while. So, yes. So,
Okay, cool.
it's promising. Yes, most probably yes. Yeah, good.
Nice. Thanks for reaching out to him.
Oh no, yeah, that's nice. I would also like to do that. Thank you. Okay, good. Khalid, it might be late, but I'll send you also the invitation. Okay, so it will be late for you in Saudi Arabia. What's the time now?
It's good.
Now it's not that bad, right? Now it is. What's the time there now?
Yeah.
8 o'clock, right?
Yeah.
Okay, 8 o'clock.
10 minutes to 8.
Yeah, 8 o'clock. Yeah. So if it is afternoon,
So,
it will be later. Yeah.
will it be the next week? Is it all week? I mean,
The whole
is
week
it a
is
break?
the whole week is a holiday.
Yeah, because you don't have it here. So,
Yeah, it is not. It's recently, right? I think we start again on November 30th, Monday.
nice.
Monday following the coming Monday. But hopefully, we'll see each other on Tuesday. Okay. We'll get an email.
Yeah, for sure.
Okay, enjoy, guys. Yeah.
Thank you. You too.
Bye-bye.
Thank you.
Do we have class tomorrow?
Thank you.
Yes, we will have class tomorrow. Oh yeah, half of all of us meet again.
Okay.
That's why you guys are. Yeah, I take it as a class, right? For me, this class is over now. Yeah. Sorry, I don't treat you guys. I treat you as numbers. Good, not good. Okay, no, I'll see you guys again on tomorrow. All of you guys on tomorrow. Yeah, okay, one more day.
Thank you.
Okay, guys. Thanks, Aliyah.
Thank you.
Bye-bye.
Correcting me.
Thanks.
You have to
See you
think
later.
about us as a particular solution, which can be added
Yeah,
to the other particular solution.
yeah. Sorry, I didn't realize you were there. It gets quiet. You're not there. It was very weird when it was Tuesday or one of the days when we had the exam.
Mm-hmm.
Everyone showed up, but there was nothing to speak. We were all quiet.
Well, at least I can bring something to the class, I guess.
Yeah. Okay.
Okay, thank you.
Take care, Jordan.
Thank you. Bye-bye. Happy
Yeah.
Thanksgiving, everyone.
Happy
Oh, yeah.
Thanksgiving, you too.
Hopefully we can meet on Tuesday. Yeah, before. Thanks.
Bye-bye. Bye-bye.
Yeah, that'd be cool.
Okay, goodbye.
Virtual pie.
Yeah, virtual. Yeah, not a virtual class, virtual hangout.
No, virtual pie.
Oh, virtual pie.
Yeah, everybody eats pie on Thanksgiving, so
That's correct.
virtual pie.
That's correct. Yep.
Okay,
Yeah.
bye-bye.
Okay.
guys.
Take care, Jordan.
See you tomorrow.
Bye-bye, Michael. Bye-bye.